Welcome to this Engineers Ireland IChemE lecture tonight. Professor Gerry Murphy will talk about the circular economy, energy and the environment. And just before we start, to say thank you to Gerry for coming. We have fire exits at the front of the room. The talk will last about 45 minutes. And after the talk, people in the room and people online can ask questions. Use the chat function there online to ask questions. And what we'll do is we'll read out the questions and Gerry will answer them. Okay, so this is both online and in person. And just to say, we had a wonderful lecture last week from Cormac Ryan from SPX Flow about liquid and gas agitation. And we hope to have some more lectures come January. So tonight, Gerry will talk to us about decarbonisation pathways, including for circular economy systems that integrate offshore wind, electrolysers, hydrogen, power to X, biorefineries, biomethane, decarbonisation of agriculture, industry and transport. And I'm happy to say I attended a similar lecture about a year ago. It was excellent, and on foot of that, that's why I asked Gerry tonight. He'll give us a wonderful overview of how all the different aspects of sustainability tie together. Gerry is a world expert in the field. He's a professor in UCC, and I'd like to welcome him back to, as a former colleague here in CIT as it was, he's welcome back to old haunts, and it's great to have him. And thank you for coming back. He's the Director of Research at MaREI, the Centre for Energy, Climate and Marine. He's supervised over 30 PhD researchers and has over 210 peer-reviewed journal articles to his name. So he's one of the top academics worldwide in terms of biofuels. So we're lucky to have such a wonderful world-class expert to talk to us tonight. And without further ado, I'll hand you over to Professor Gerry Murphy.
Thank you very much, Cillian, and thank you for the invite. So the topic is the circular economy, energy and the environment. So I work as the director of the MaREI Centre, and we have graduated 220 PhDs in the area of energy, climate and marine. It's quite a broad centre. It's been in place since 2013 and it ends in December 2025. So I've been freed. I don't have to run this organisation anymore. It's been a huge pleasure. It's been a fantastic journey. It was a very broad perspective. So we had chemical engineers, electrical engineers, ecologists, air quality, society, community. So we had a very broad lens looking at some what we would consider grand challenges in the area of decarbonisation. One thing I found is that before the MaREI Centre, if I wrote a paper, it was me and a PhD student. Now, when I write a paper, there are 12 names on it because we have different people with different perspectives. So we have this multi-lens perspective. Let's look at the problem. So for example, we're looking at offshore wind, and we were involved in the designated marine area plans. We looked at the puffins, we looked at the seals, we looked at the dolphins. We did some work on seaweed biofuel. We were down in Sheep's Head, the Dahlia Murraku Marine Research Centre with people who grew seaweed. So we really went to make sure that we got all the perspectives on a problem. And I would say, like, to solve problems, you have to get outside your silo and get lots of different perspectives. So it's been a great journey. It took 10 years of my life. It aged me by 20 years. You'd never think I was 25. So this is a subsection of the MaREI Centre, and I work in this with some great colleagues, Arkisman Bose, a chemical engineer, Richie O'Shea, an energy engineer, and David Wall, who would be a civil engineer. So the four of us sort of work in a co-op of, we bring all our researchers together, we meet every Monday morning, we trash out problems, and this is where we see ourselves in the circular economy, energy and environmental systems. But we started off really with biofuels and biorefinery, and then we started looking at microalgae and biofertilizers, and then we started looking at biochar, and then we began integrating electricity into our fermentation processes. So we're into bioelectrochemistry, and we look at e-fuels, e-refineries, and we do a lot of work at the moment in what we call power to X, and that's using electricity to make hydrocarbons. So we look at hydrogen, methanol, ammonia, methane, we look at biochemicals. So it's a broad church with lots of involvement. I think what's interesting is when we look at decarbonisation, because this was the big challenge of our centre. We're going to have offshore wind, and how do we bring that into society and see the impact? What I find interesting, I'm not an electrical engineer, is that at the moment we're averaging about 40% renewable energy supply in electricity from onshore wind primarily. And we have experienced a world record in system non-synchronous penetration. Now, this means the ratio of variable renewable electricity to our demand. And that's at 40%. And we're heading for 80%. That's our target for 2030. So we're already at world record level trying to manage a grid, and we're an island grid, and that's the challenge. We can't plug into France next door or Germany up here. We are an island. So this is a huge challenge for us. And EirGrid, who we do a lot of work with, are very, very good at what they do, but they're very, very challenged. And the amount of money we're going to spend on the grid will be extraordinary. For example, now I'm no expert in electrical engineering, but you have to manage the voltage and inertia. They built a 130-ton synchronous condenser, which is a flywheel, purely to manage the frequency in the electrical system. And that cost 150 million. So it's not producing energy. It's purely to manage the wires. While we have this offshore wind, the variable renewable electricity, we have a target for 2030 of 17 gigawatts of offshore wind. We already have about 6 gigawatts of onshore wind, and the country has never used more than 7. So we've used, at max demand ever, 7. We have 6 of onshore wind. We're building 17 of offshore wind. So when they're all blowing, we're going to have an awful lot of electricity. But for 2030, which is 5 gigawatts of offshore wind, that's our 2030 target, that costs 25 billion. So for us, for each home, it's about 25,000 to put those devices in the water. When we continue to look at, when we continue to look at other things we're meant to do, so we're meant to electrify transport, we're meant to purchase 945,000 EVs, and we're not meant to have internal combustion engines anymore. That's another 28,000 per home. And then we're meant to deep retrofit. So we're meant to move out of our houses, re-insulate, underfloor heating, heat exchangers, average about 60,000, but you're also out of your house. You're in someone else's accommodation while they do up your home. I was looking at a thing yesterday online. They reckon that 90% of the insulation put in the UK is wrongly put in. There's 130,000 heat exchangers being called back in Ireland. So like we are employing technology that really isn't all that mature, and the workmen or the craftspeople aren't that well up on it. But we have a huge requirement, and that's another 60,000 per house. So when you add up cars and retrofitting your house and offshore wind, it works out at about 120,000 per home. And that's the easy bit. That's what we call easy. Like we know what to do. Then we get to the hard to abate sectors, and that is cows. 38% of our greenhouse gas emissions come from belching cattle, belching methane. Methane has a global warming potential 28 times worse than CO2. It also comes from ships, planes, trucks. Like, we're not going to have a battery on a plane. You're never going to have a battery on a plane, ever, ever, ever. So it's going to be hydrocarbon. We reckon that we can run trucks for about 400k on a battery. But after that, we need a hydrocarbon. So we need to make fuels. And this is really the realm of chemical engineering. And we also have cement production, and we have steel production. Electricity is 20% of energy. So if we have decarbonized electricity, we've only got rid of 20% of emissions. There's the other 80, which is industrial heat and which is transport. So we have lots of challenges. And this is our menu. This is what we look at. So I'm going to go in and out of this little menu as we go along. I'm going to start at anaerobic digestion because it's probably where I started. So we're looking at a sort of a biological process where we take waste matter and we convert it into biomethane or biogas, which can be used for electricity, heat, or transport. And now we have a target, and it was quite interesting. I do a bit of work with the International Energy Agency. I spent a month in Paris last year. And when the war started, it really brought home to me, there's no climate emergency, there's none. It doesn't exist. There is an energy emergency, because once the war started, we were contacted. The guillotine will come down, the gas is gone. Austria depends on Russian gas. What do we do? And we did a bit of work at the time thinking, we actually looked at a particular dairy facility, and we drew a circle of 10 kilometers around it. We thought if you digested everything, if you got the slurries and the grasses in that 10 kilometers, you would replace the natural gas. So we're sort of thinking, what would you do if it happened to you, if there was no gas coming? And a lot of facilities are dependent on gas. What's interesting, we get twice as much energy from the gas grid as the electricity grid. And a lot of the gas grid is used for the electricity grid in an Irish context. So natural gas is really, really important. And because of that, the EU have said that we will have 10% of our natural gas from biomethane by 2030, and it will ramp up. So at the moment, we're at 1%, so they want a 10-fold increase by 2030. In our climate action plan, it's there. Like if we don't do it, we don't meet our climate action plan. And at the moment, we're heading for a fine of 20 billion in 2030 for not meeting our climate action plan. So if we don't have all those wind turbines in the water in 2030, and if we don't have all those biomethane plants built by 2030, we're going to be spending 30 billion on fines. So the fines are based on having these, and the chances are we won't have them because we haven't started. There is no remuneration scheme. If you build an anaerobic digester now, there's no way of making money. There's a very good, I'll be careful, I'm online, there is biomethane plants selling less biomethane this year than last year. Some of them have severe financial difficulty. So we have all these lovely targets, but we're not looking like we're going to meet them. I work, as I said, a bit for the International Energy Agency. I led this task for 6 years, and we produced lots of reports. So the one on the right, far over, integration of anaerobic digestion into farming systems. And Italy has this fabulous biogas done right system, and it's sort of minimizing the carbon footprint of agriculture. They don't plow the land. It's no-till. They have a crop, say it's corn, but then they have a catch crop. So there's another crop, which is to make sure there's no bare earth. They don't want bare earth. So when you take down the corn, feed the cattle, there's grass. And they cut the grass and they put it in the digester, and the slurry goes into the digester, and they minimize their carbon footprint. And they also have biogas, and they also have fertilizer, because the byproduct is a fertilizer replacing fossil fertilizer. Another one I'm quite interested in, and it gets no media attention, I don't know why. Part of Repower EU, which is the EU's action plan, is 25% of all farming is organic by 2030. I don't think many farmers would be aware that 1 in 4 hectares in Europe, including Ireland, is meant to be organic by 2030. And we visited this farm. There's no fertilizer. What happens if you have no fertilizer? You have no growth. So they're building digesters with only organic produce going in to produce an organic fertilizer to increase the growth. And then the biogas is secondary. It's like, oh, we have biogas. But they're doing it for fertilizer. So they're increasing the yields on an organic farm by making a biofertilizer. So we would see this 25% of agricultural land that's meant to be organic by 2030 all having digesters, or else they don't have growth. Because if you don't have a fertilizer, you're not going to have growth of your crops. They've been certified as greenhouse gas negative per litre of milk. So they have a greenhouse gas negative milk product from that farm certified. So that to me is fascinating, because farmers are being beaten over the back with a stick because, oh, you have to reduce your emissions. And I think we need to offer pathways. And this is a pathway. Another element that's very important is when your methane goes in the gas grid, the CO2 is left behind. And that's almost 99% pure CO2. It's very cheap because it's a byproduct that's there, because you put methane in the grid, you've taken out the CO2. And if you think about carbon in terms of, we need carbon dioxide, we require in Ireland about 50,000 tonnes of CO2 per year. We put it into abattoirs to numb animals, we put it into drinks, we have it in laboratories, we have it in hospitals. So we can make a biogenic CO2. During Brexit, there was a big problem. They couldn't slaughter animals because an American fertilizer plant left Britain. And the way we get CO2 at the moment is we get it from the ammonia process. We convert natural gas to hydrogen, Haber-Bosch process. CO2 is a byproduct. We take that and we put it in our drinks and we put it in our slaughterhouses. That Haber-Bosch process was asked to come back into Britain because they couldn't slaughter animals. If you don't have CO2, you can't slaughter animals. So we can have a sustainable biogenic source of CO2, and that CO2 we reckon will have more value than the biomethane in the next 10 years because we need sustainable CO2 to make sustainable hydrocarbons. So if you're going to make a fuel with renewable hydrogen and renewable CO2, where is your CO2 coming from? It's going to come from anaerobic digestion. And then we've looked at converting methane to methanol. And methanol is methane with an extra O, oxygen. So CH4 is methane, CH3OH is. So we can make methanol, and methanol is a liquid, and it can be a liquid fuel, or it can be a precursor to formaldehyde, to green chemistry. It's also a shipping fuel. So how can we optimize production and maximize sustainability of biomethane? So a lot of reports would say that biomethane is not sustainable. I forgot to stop my watch. That, you know, CO2 goes into the atmosphere, you leak methane. One of the things we're looking at is putting a big box around the biomethane plant and saying nothing is leaving. We're going to get value from the CO2. We're going to get value from the digestate. And this is a process we've been looking at. It's conversion of carbon dioxide and biogas to microalgae. So I like this one, and we're applying this in Dingle. Biomethane is quite expensive, and you need to have economies of scale. Well, we're saying this is a small digester, and we'll grow microalgae off the CO2. So we've developed this technology. It's my good colleague Arksman Bose is running with this now. We've got projects on this. So we have a little tower. It's a carbonate bicarbonate tower. pH is around 10. We put the CO2 in, and we get this carbonate bicarbonate cycle. And we put microalgae up, and the microalgae take out the bicarbonates and use it to grow and give back carbonate. So in effect, your biogas, which is 40% CO2, 60% methane, is going into a tower. Pure methane comes out one side, and the microalgae come out the other, and they grow. And microalgae have, we buy this at home. My wife likes to make these, I'm thinking of milkshake, smoothies. So she makes these smoothies with cacao and spirulina powder. Truly awful, but it's very good for me and the family. But it's $3.89 for 100 grams. That's 39,000 a ton. So we're looking at this project in Dingle. They want the biomethane in the tractors, small scale, anaerobic digester, and we can have a microalgae product. So we're looking at really intelligent people being highly paid, working down in Dingle, biorefinery, microalgae, and biomethane, running their tractors. They pay $1 million a year for their food waste go to Waterford. It'll stop in their own digester. All their slurry will go into it. They're looking at a slaughterhouse, and the digester allows them to have a slaughterhouse because the byproducts go in here, the food waste goes in here. They get microalgae, they get biomethane for their tractors, and they can have a slow food movement. They want to say, you're eating Dingle beef and we're charging you €2 extra because it's Dingle beef. At the moment, it goes into what they call the mainland, and they don't know where the beef came from. So this would give them a small abattoir, sheep's wool, microalgae, tractors running on biomethane, biofertilizer, circular economy. It's led by Dinny, and they're all very happy with this as a concept. Many things you can do with microalgae besides eating it, but it is a very important product. Then we're looking at the digestate. So you get this liquid digestate coming out. Typically, you put it on agricultural land. It's a biofertilizer. Sometimes there's too much of it. So we've been working with the distillery, very large distillery in Middleton, and we're looking at anaerobic digestion, but there's so much byproduct that you're now doing nutrient management balance on hundreds and thousands of hectares of agricultural land. I worked on a pig farm in Offaly about 20, 30 years ago, and we had to go for planning in 3 counties with the slurry from the pigs. And we had to do a nutrient management balance on every piece of land. So it can be easy to say, we'll treat the digestate so we can separate it into liquid and solid. The liquid can go into hydrochar, and the solid can go into what we call biochar. So in effect, it's pyrolysis. We have a muffled furnace in our lab, and we convert that wet digestate into char. And that char, you can see it there under the microscope, it's about 90% carbon. and it's fixed carbon. And if you put that on the land, it's called a negative emission technology. In effect, you've sequestered carbon, it's fixed, it goes on the land, it increases photosynthesis, pulls more CO2 out of the atmosphere, improves soil health, improves yield, and it's a negative emission technology. So go back to your farm. If they do this in the farm, they get more negative certified emission. It's allowed in the Renewable Energy Directive. So there's an equation which includes for this as a soil sequestration. So rather than pulling CO2 out of the atmosphere, burrowing down half a mile and putting CO2 as a gas underground, you're putting it on the land, increasing photosynthesis. Farmers are happy. I have a picture of the next slide. Again, it's like a black soil. Another thing my wife buys, activated charcoal for digestive discomfort. And it sells in my local shop for 16 euros. We have it at home. That's 1.3 million euros a tonne. So what we want to do in Dingle is they'll make microalgae and they'll make char. And they'll sell char to the local supermarket and we'll all have healthy bellies. And then we'll drink microalgae and it's a super vegetarian food. So again, these are things we're looking at. And we've made char from many different materials. So we've operated at 300 degrees, 400, 500, 600, 700. We have a Taguchi design of experiment. We've used digestate, we've used willow, we've used barrels. We've made chars. The ramp-up rate has varied from 4 to 10 degrees Celsius per minute, the holding time. So we have a whole matrix of solutions, and we get very different answers. And we published this recently in the Royal Society of Chemistry. So we're looking at all the things you can do. And what you can do, we've been straining out ibuprofen. Put ibuprofen in water, through by the biochar, nothing comes out. We've been doing PFAs, the forever chemicals. So we can see biochar as a means of removing contaminants from water. It can go on soil. We also find it's very, very conductive. So we can get higher levels of conductivity. So for example, in this biochar, we had 400 meters squared of surface area per gram. I find that incredible. Like my house is a big house. It's 2,000 square meters. No, it's not. It's 180 square meters, 2,000 square feet. So double the floor area of my house up and down in a gram. So we can have loads and loads and loads of pore space. We can also have conductivity. For example, this is a piece of work we did. We worked with the distillery. We looked at byproducts. And we had chars at different temperatures. So we had it at 300, 500, 700. And we digested byproducts. And you can see that no biochar is that black line. The biochar at 700 degrees Celsius, so the higher the temperature, the more surface area. The lower the temperature, less surface area, but higher conductivity. So what we found was it wasn't the pores, it was the conductivity. So we found that the biochar at 300 degrees Celsius significantly improved the biomethane production because of the conductivity. It's like an electron bridge. So for adding to anaerobic digestion, we would recommend pyrolysis at low temperatures. For removing contaminants, we would recommend pyrolysis at high temperature. So we're trying to create this matrix of how can we tune the biochar, and then what are we using the biochar for? So we do a lot of work in anaerobic digestion, and we decided, well, we've done a lot of work on reactor design. And for us, it's a two-phase system. So the first phase is at a pH of 5.5. So if you start off with complex polymers, say grass, and then it's sort of liquefied. If you put grass in a barrel at the bottom of the garden and go down in 2 weeks, it's liquefied. Then it ferments. And all that happens at about pH 5.5. Then the next process, which is the methanogenic process, they're archaea, they're not bacteria. That happens at 7.5. So we're fans and breaking the process up into two chambers. So we did a bit of work. This was Shui, one of my very, very bright PhDs. And we sort of looked at single stage, two stage, with biochar, without biochar. So that's the design of our experiment in the bottom right. So if I look, for example, so H1 is at a low pH, M1 is at a neutral pH. So we're trying to have all of the acidy phases first, and then make methane with the archaea in the separate phase. So bacteria in one chamber, methane, archaea in another chamber. So M3 is a single stage process. H1M1 is a two-stage process. And you can see over in our charts that the M3 is always less than M1. So M3 is sort of a light sandy color. M1 is a bluey color. So the blues are always higher than the browns. We get more methane. And the reason we get more methane, we realized, is that H is where we have the bacteria at the low pH. The dark red is H2, the light red is H1. We get more volatile fatty acid production. So we found that biochar at a low temperature in a fermentation increases the fermentation rate, gives us more hydrogen, more volatile fatty acids that go into the second chamber and make more methane. So that was interesting. That was a nice learning. And that there's the char. So you can see what it looks like. It's like coke. It's black. It's pure carbon. We then thought, what about sticking electrodes in here? Why not put a bit of a cathode and an anode inside in the anaerobic digester? So here we have 5. This is Shui again. Shui just left me and got a job in UCD. I'm upset to say. She was fantastic. 5 reactors. The one on the far closer to me, what would that be if I was up there? That's on the right. So we put in grass and slurry, typical anaerobic digestion feedstocks. We have a reactor that's producing group 5, 193 litres of methane per kilogram volatile solid. So that's the normal anaerobic reactor. In number 4, we put in biochar. We got more methane because it helped the process. But then when we stuck in electrodes, so this is a graphite electrode, and in particular group 3, we broke up the electrode, making it very, very rough. We doubled the methane output. So what we found happened is by putting an anode and a cathode in an anaerobic reactor, at the anode, there was more breakdown of the feedstock. There's only 1 volt, by the way. This isn't major electric current, it's a volt. We got increased degradation. Electrons went over to the cathode, reacted with the CO2 and the biogas, which is in the chamber, and made more methane. So the methane composition in 3 was about 90%, where the methane concentration in 5 was about 55%. So in the reactor, CO2 has been converted to methane, and we doubled the methane output. So we have this target to replace 10% of natural gas with biomethane. We're now saying we can half the feedstock, because we'll get double the methane from a given feedstock by putting in 2 little electrodes. Now we're doing more work. We're now, and this is part of this paper. How far back? This paper, Royal Society of Chemistry, we're now 3D printing electrodes with char. So it'll be bioelectricity because it'll be alive. It'll be 400 meters squared per gram. We'll make that char at 700 degrees Celsius, and all these bugs will be living inside in the electrode. We'll have this extracellular polymeric substances all around it. So that's our next step. And that's a really beautiful circular economy. So your digestate is converted into char. We print the cathode, we put it back in the electrode, and we double the output of methane. So that's part of our integration of electricity with anaerobic digestion. So now we're moving on to offshore wind, and we'll work our way back again to fermentation processes. So we wrote this report for the International Energy Agency, Circular Economy Approaches to Integration of Anaerobic Digestion with Power to X Technologies. And when we talk about X, when X is equal to 1, it's hydrogen. So we split water in an electrolyzer, very, very simple. We have to get rid of fossil hydrogen. And we have to get rid of it by making renewable hydrogen from offshore wind, from PV, from electricity. We split water into hydrogen and oxygen. X equal to 2 is methane. So we get some form of biogenic CO2 and we react it with hydrogen and we make methane. And again, we produce twice as much energy from the gas grid as the electricity grid. So we need renewable natural gas. We can't have fossil natural gas. Then we go on to methanol. World demand is 110 million tons in 2021. We need renewable methanol. We need renewable ammonia so we can make green fertilizer. So hydrogen from offshore wind, N from the atmosphere, Haber-Bosch, green fertilizer, not fossil fertilizer. So when you put fertilizer on the soil, it's natural gas. You're putting natural gas on the soil. And in a net zero world, there shouldn't be natural gas and we shouldn't have fossil ammonia. And we have a lovely 200-acre site sitting in the harbour that used to make natural gas from offshore gas. Our thesis is stick an electrolyzer there and make green ammonia, and there's a train track behind it, and make green fertilizer and help the farmer. So the farmer will have carbon neutral fertilizer, biochar on the land, organic farm, anaerobic digester, and we're looking at a pathway, an offer to try and have sustainable farming. And then we fisher troughs. And that's leading us to SAF, sustainable aviation fuel, and renewable diesel. So we're trying to decarbonize all of these fuels. Again, I've shown you this, but what I'm most interested in, these little shady areas are where we're putting in our wind farms. We've already auctioned off Dublin, and the idea is that electricity off Dublin goes into Dublin and feeds data centres and feeds Dublin. But when you look down south off Cork and Waterford and Wexford, we're looking at maybe 2 gigawatts. We don't have the capacity to take that to Dublin. I mean, the grid isn't strong enough. The wires aren't big enough. So that phase 3, you can see those 2 little orange guys, they're non-grid. So we will bring electricity ashore and it will not go into the grid. The idea is that, in particular, we expect a gigawatt to come into Cork. Cork uses at most 0.3 of a gigawatt. The wires could take 0.3 to Dublin, but we're not sending it to Dublin. So we have this challenge. What would you do if it happened to you? An energy park, data centres, hydrogen, ammonia, methanol, shipping fuel. We also look, and we set up a company called Cork Biomanufacturing. We can make proteins from offshore wind. So hydrogen, CO2, onto acetate, onto protein. So we can make protein. I think that protein would be more for cattle than for humans. I mean, I think Italy has already banned alternative proteins, but there's a whole market in new proteins, and this would be a way. So we have all these options that we could do in Cork. So X is equal to 1. We are going to have an electrolyser. There will be an electrolyser in Cork. And the idea would be this will be a new energy park. There'll be loads of renewable electricity. There will be hydrogen. There's 2 gas fields. Well, there's the gas fields. We can store hydrogen in the gas fields. We could take your CO2 and put it in the gas field. So it's an offering for industry. Come into this fabulous energy park and everything will be there for you to be a net zero industry. So if we look at integration of hydrogen with biomethane. So again, a lot of my work in the past was in anaerobic digestion. And you can see if I pick one of them, species 4.1, it's an archaea. 4H2 plus CO2 gives us methane and water. So I found that quite interesting. So we had our anaerobic digesters and we just stopped giving them slurry and grass and only gave them hydrogen and carbon dioxide. And what we found is that all of a sudden we were dominated with Methanothermobacter wolffi. And wolffi is the Latin for tungsten, and they like a little bit of tungsten. They work better. But we were now converting hydrogen and carbon dioxide to methane. And we ran little batch reactors, and then we ran some larger reactors. And we found in the process engineering, hydrogen doesn't go into solution readily. We had to put it under pressure. We had to recirculate it. So we devised the system based on one reactor. We modeled it, so we varied the composition of the reactors, and then we made this. So this cost us a lot of money. It's a little demonstration scale. So under pressure, we were introducing hydrogen and carbon dioxide into R1, under pressure, then into R2, then into R3. And if you look at this side, which I think is the left, you can see R3 was almost pure methane. So we're now converting CO2 to methane in what we call an ex situ biomethanation rig. So it works. What we modeled works, and all we're doing is 4H2 plus CO2 is methane and water. So we're doing what has been done by these archaea since time immemorial. Long before humans walked the planet, before the dinosaurs, those archaea were doing that. And they're very happy to do it. And it's exothermic. It gives off heat. It works. It should be no shock. I mean, the patentable stuff here was the way the rig was set up. So why would you do it? Why? I've been asked, why would you want to convert CO2 to methane? Why? So this is our next piece. We're looking at application of power to methane at a wastewater treatment plant. One of the challenges we have, because we're an island, is we dispatch our spill electricity. So the target for renewables for 2030 is 80% renewable electricity, 51% emission reduction. But, and this you have to consider, we're at 40% renewable now, and we have to spill 14% of renewables. So in the middle of the night, if we've 17 gigawatts blowing, we've never used more than 7, we're all in bed, we don't have air conditioning, there will be lots of electricity. And the idea is we would convert that to hydrogen. What tends to happen in the energy market is in Copenhagen, for example, they have negative pricing. And what happens at negative pricing, all the turbines are blowing. They have a little bit of fossil fuel. If you tell a combined cycle gas turbine to go offline, they charge you money. So you're told if you can use that electricity, we'll pay you, because otherwise we're paying a big power plant to go offline. So there's negative pricing. And I visited a plant in Germany, and they paid an average 1 cent a kilowatt hour for their electricity because they were taking electricity that would otherwise have required a power plant to shut down. So we're looking at getting electricity when it's cheap, when it would be curtailed or dispatched down. So we looked at, I was part of a design team in 1992, Cork Main Drainage, Carrick-Grennan. I haven't been there since. So I designed the anaerobic digesters. I was involved in the storm overflows, never been there. So we thought, if you wanted an electrolyser in Cork, where would you put it that people wouldn't complain? The wastewater treatment. Anyone here been to Carrick-Grennan? Up one. So it might not cause people to object because they might know it's there. It's something out there. They've never been there. So we thought, let's put an electrolyser at a wastewater treatment plant. And the idea would be the oxygen could feed the aeration basin. So rather than pumping air, you pump oxygen. It's 5 times less volume, 5 times less pumping. It reduces considerably the power footprint of the wastewater treatment plant. And we figured out we needed 7 million meters cubed of oxygen, and that's a 10 megawatt electrolyser. And that was equivalent to 10% curtailment of a 144 megawatt offshore wind farm. So we're taking curtailed electricity. The oxygen in splitting the water is going to our wastewater treatment plant. We'll have twice that amount as hydrogen because it's 2H2O. So we have 14 million meters cubed of hydrogen at the electrolyser. And we thought there's a biogas plant there. I designed it. It's converting sludge to biogas, and that's as far as it goes. So we could use our ex situ biomethanation and convert the biogas to pure methane, and all the CO2 will become methane. So you can see here we have 1.4 million meters cubed of methane from the sludge digester. We had 776,000 meters cubed of carbon dioxide. That becomes methane. So you're upgrading, but you're also increasing the methane. And we could run 94 compressed biomethane trucks, and we could run 300 compressed hydrogen trucks. So we're now changing what the wastewater treatment plant looks like and sort of upping the value and having a circular economy. Now, I'll come back to it later. We'd also look at our biochar being used to upgrade the wastewater to potable water to put into the electrolyser. And this is a plant outside Copenhagen. Biochar is the name of the plant. It's a wastewater treatment plant. And at that wastewater treatment plant, they have 125 meters cubed of biogas per hour, of which 50 is CO2, 75 is methane. So with the ex situ biomethanation, that 50 meters cubed of CO2 becomes 50 meters cubed of e-methane. So you've now got 125 meters cubed of methane. You've got pure methane. You need 4 times the amount of CO2 as hydrogen. So you need 200 meters cubed of hydrogen. Hydrogen is 3 kilowatt hours per meter cubed. You need 600 kilowatt hours of hydrogen. An electrolyser is about 60% efficiency. You have a megawatt. 1 megawatt electrolyser giving you 600 kilowatt hours of hydrogen, upgrading 50 meters cubed of CO2 to 50 meters cubed of methane. So it's a nice, tidy process. And now your biomethane could run a truck, where before it couldn't run a truck. So you've increased the exergy. We would see as heat as lowest value, electricity next, highest value is transport fuel. So then we're looking at, well, how does it all fit together? So the integrated circular economy system. For example, in Denmark, we've been working with, it's called Nature Energy. It's been bought out by Shell. They have these really large digesters. They bring in about 600,000 tons of dung and slurry and food waste. They have catchments of about 25 kilometers. They have pipelines. So farmer goes to sump, drops in slurry, screw augered, 25 kilometers into the digester. So at the moment, they are replacing 39% of natural gas on a year-on basis with biomethane. So they're way ahead of the posse. But if you put an electrolyser and an ex situ biomethanation at those facilities, you're increasing the methane output by about, all the CO2 is going to become methane. So they'll be at 65% green gas by putting an electrolyser and an ex situ biomethanation at their digesters. Now, the joy of this is they have about 12 of them, but they're massive. So it's only 12 systems, and they've increased their methane output by about 60%. Methanol. So we've been looking at Cork as a concept. So Irish distillers have 50,000 tons of almost pure CO2 as a byproduct from fermentation. We will have anaerobic digestion in the harbour. It may be that we digest the byproducts from the distillery. So minimum 50,000 tons. So that was sort of the basis for this thing we were thinking about. Then you'd have an electrolyser. You'd produce hydrogen and you'd react the hydrogen with the CO2 and you'd make methanol. And there's two ways of making methanol. One is reforming biomethane. So at the moment, Maersk, who are responsible for lots of shipping, are going to Denmark and saying, we want your biomethane. They're converting it to methanol, and they've built 20 tankers to run on methanol, and they can't find the methanol. So they've gone to Denmark and said, we'll take your biomethane, reform it to biomethanol, put it in our ships. There's very, very high standards in shipping. And what's interesting about shipping, every country has a vote. Every single country has one vote. And they've decided that shipping will be carbon neutral by 2050. And it's roughly off the top of my head, it's about 20% decarbonisation by 2030. And you have to do it. It's the IMO. So there is a demand for methanol. And methanol, we already have 110 million tons for other things. We're going to have the same again for shipping. So it's happening. Methanol is a liquid that will be used in ships. The other one is e-methanol. So carbon dioxide and hydrogen gives you carbon monoxide and H2O. Carbon monoxide and 2H2 gives you methanol. So we have two ways of making methanol. Convert biomethane or hydrogen from offshore wind and biogenic CO2. This is Maersk. They have a whole document about zero carbon shipping, and it's either methanol from biogas or liquefied biomethane. Green ammonia. This is a facility in Cardiff. I need to hurry up. Haber-Bosch hydrogen ammonia, green fertilizer. Fisher troughs. We've been struggling a little bit with this, how we deal with all the different components. When you have Fisher troughs, only 68% is liquid, about 34% is diesel. You have waxes, you have gases. We're struggling with allocation methodologies to try to figure out how you put a value on the piece. We want Fisher trough diesel for shipping. Celtic Cluster, Lower Harbour, Urban Oil, ESB, gas networks. The refinery wants to go green. We'll have a gigawatt of private wire coming in. We have gas fields where we can store CO2. They want to make biofuels, hydrogenated vegetable oil, SAF, decarbonised ammonia, methanol, e-fuels. There's planning permission, I understand, for an ammonia combustion facility, so you can make dispatchable renewable electricity from ammonia that was electricity and is now used when the wind isn't blowing. Dunkelflaute. We tend to get 20 days of no wind in the winter, and what do you do during Dunkelflaute? You make something, you store that something, and you use it for the 20 days. So we've done a little bit of maths. So we're looking at our 50,000 tons of biogenic CO2. We're looking at power to methane. We found, with very simple stoichiometry, a 70 megawatt electrolyser. So we used a 70 megawatt electrolyser for our analysis. And methanol requires more CO2, so we need an anaerobic digester. Ammonia needs no CO2. Fisher troughs needs extra CO2. So we've done the maths. What's interesting, because we have a project with colleagues in America, they're trying to model the electricity grid. If you have 100 kilowatt hours of electricity, you make 65 kilowatt hours of hydrogen, 54 of methane, 55 of methanol, 50 of ammonia, and only 20 of Fisher troughs diesel. So we've sort of done the maths, what sizes they'd look like and what they'd cost. What's interesting, this is a paper we're going to submit in the next few days. This looks at shipping fuel in 2050, 705 terawatt hours is the target. So if we wanted all that to be decarbonised, you'd be looking first of all at cheap CO2 from biomethane or ethanol or whiskey. After that, you go to biomass combustion, so wood chip burning, and that's more expensive because you have to get rid of the nitrogen. And after that, you're going to direct air carbon capture. So biomethane, we reckon, is about 30 euros a tonne. If you go up to the Midlands and go to the wood chip facility, that'll be about 80 euros a tonne because you have to get rid of the nitrogen. And then direct air carbon capture, pulling it out of the air, 450 euros a tonne. So what we found, that little red line there is Fisher troughs diesel, which is only getting a 20% return. So it requires lots of CO2. So it uses up all the biogenic CO2 very quickly, and then it's buying direct air carbon capture. So we found the average value for Fischer-Tropsch diesel is 311 euros a megawatt hour. That's 311 per ton of diesel equivalent without taxes. So 3 euros 11, where methanol is about 117, because methanol is very efficient, and we would have enough biogenic CO2 from ethanol, from whiskey, from biomethane if we do what we're meant to do. So if we build all the biomethane plants we've told we do, that CO2 would allow us to make shipping fuel to the level of the demand for shipping fuel. So that's only 1 euro 17 per litre of diesel. So methanol is cheap, requires small amounts of CO2. Fischer-Tropsch is very, very, very expensive because of all the other elements there. So this is our sort of biofuel, biorefinery, e-fuel, e-refinery. We based it on a distillery, or it could be a creamery. It's a food and beverage industry. They're making their product. We take their byproducts. We would suggest a 2-stage fermentation, dark fermentation, and then methanation. We would take or digestate and make char. We'd put the char back to a wastewater treatment plant. We'd upgrade the contaminated water to potable water. That goes into the electrolyser, producing hydrogen that reacts with the CO2. And we now make methanol, or Fischer-Tropsch, or ammonia, or methane. We also looked at duckweed from the digestate to replace the spillage. Sorry, the distillery produces a feed, which is fed to cattle. So we thought the duckweed, we can feed the cattle duckweed because we've used all that to make energy. So it's a sort of a refinery, e-refinery, biorefinery. We can also make volatile fatty acids in that dark fermentator. We've also made caprioic acid in our MES systems, which is another topic. I'm nearly there. We did a few papers about heavy transport. So this is heavy transport. So we can't electrify everything. And this is what I want to get across. So the best model would suggest that electricity can get to 55% of energy. At the moment, it's 20. So if we tried to electrify all our cars, as many trucks as we could, our houses, we'd have 45 left. And that would be industrial heat. You can't make glass without gas. You have to have a gas. Planes will always have a liquid fuel. Ships will have a liquid fuel. So what we looked at here is these fuels. And down here on this, at the 00, that is the nadir. It's the worst place you want to be. And down there you have lithium ion. Very voluminous, very heavy. And up at the top, you have utopia. Not much is up there, but you can see the best ones are jet fuel and diesel. So they have quite compact energy. We looked at a lithium-ion battery for London to Dubai. The battery would be 5 times bigger than the plane. So you're not putting a battery on a long-haul flight. You might get Cork-Dublin, but you're not doing any long-haul. So we realized we need to get these methanol, Fischer-Tropsch. We need heavy fuels. They have to be renewable. One of the things we looked at is, this is in Sweden. They ran the bus service of biomethane from slaughter waste in Linköping. Linköping is about the size of Cork. Slaughter waste, slurry, into the digester, ran it into the buses. All the buses run off biomethane, digestate to the land. They lost the contract. In came electric buses. Electric buses from China replaced Scania and Volvo and the circular economy. And TV crews came to take photographs of the electric buses from China. So Volvo and Scania were left out. The electric buses then were freezing because it's minus 16 up there, and they'd get in a fossil fuel burner in the bus so people could be warm. So they weren't all that happy. But within a year, they had replaced it by liquefying the biomethane, cryogenic, about minus 173, 12. And these trucks run 1,000 kilometers in one fill. And again, it's Sweden, they have Scania, they have Volvo. Nothing else will take you 1,000 kilometers on one fill besides this cheap biomethane, because it's coming from slaughter waste, it's coming from slurry. There's no other value for it. We then looked at batteries, fuel cells, or engines for heavy commercial vehicles. We found a battery would work up to about 450 kilometers. After that, you have 2 choices. You stop and you plug in your truck for a few hours, or else you stop. So we found that after 450 kilometers, because I was over in America last week, and they're saying truckers do not do 450 kilometers. They do 1,000 miles. They just keep going. They're not stopping. So then you'd have to have a hydrogen fuel cell. So our thesis is hydrogen fuel cell beyond 450, under 450, a battery. We looked at deep sea shipping. And the problem with deep sea shipping is they have massive fuel storage. It's a heavy fuel oil. They can circumnavigate the Earth once or twice. So if you bring in an e-fuel, you're going to have to stop because it's more voluminous. So all of a sudden, rather than just going from Shanghai to Rotterdam and keep going, they'll have to stop somewhere along the way. So you have to change the operation of the deep sea shipping. But again, methanol. Methanol is the fuel of choice. The last one we looked at, and this really sort of impacted on how hard it is to decarbonize, we looked at aviation. And what's interesting, which I didn't know before the paper, which is the idea of research, 2% of CO2 comes from aviation, but 5% of warming. So you're up at 30,000 feet, you've got a contrail, you've got particulate matter, and that contrail, and Eamon Butler, my good colleague, doesn't believe me, but evidence is there. 3% is contrails radiating, trapping heat. So if you replace sustainable aviation fuel or jet fuel with sustainable aviation fuel, you haven't got net zero aviation because you still have contrails and you've still got warming. So you spend all this money, about 5 times the cost of jet fuel, put it in a plane, and you reduce the problem by about 50%. So you'd actually have to have jet fuel, sustainable jet fuel, and direct air carbon just to pull CO2 out of the atmosphere in an accountancy process. So what we found, the cheapest way to decarbonize aviation was burn jet fuel, do a calculation, and say to them, you have to pull that out of the atmosphere with direct air carbon capture and put it underground, which is a very sad output, but that's the output we got because there was so much energy required pulling CO2 out of the atmosphere, direct air carbon capture, 450 euros a ton, finding your hydrogen, really expensive fuel, and you're only having the problem. So that was sort of depressing. But that's what the hard-to-abate sector is because, for example, renewable fertilizer also only halves the problem because when you put fertilizer on the soil, you have nitrosomanus and nitrobacter, and they give off N2O, and N2O is 273 times more warming than CO2. So making renewable fertilizer is half the problem. Making sustainable aviation fuel, halving the problem. Net zero is a folly. That's me done. Thank you.